Question 51. Show graphically that y1 of x is equal to x square and y2 of x is equal to x mod x are linearly independent on minus infinity to infinity. However, wronskian vanishes for every real value of x. So we have two functions here. y1 of x is equal to x square and y2 of x is equal to x mod x. So the first part asks us to show these two functions are linearly independent graphically. So y2x is x mod x. So we know that this can be written as x square for x greater than or equal to 0 and minus x square for x less than. Function can be written like this: x less than, for all values less than x less than 0 the function is same as minus x square, and for all values greater than or equal to 0 it becomes x square. So graphically, if we are to show, it will look something like this. So this is, let this be xy axis, and now y is equal to x square for so So y equal to x square will look something like this, and y equal to x mod x will look, this part will be same, so this will look this part, and so it will look something like this. So y equal to minus x square. For x is, when x is less than 0, y value is negative, so it will look something like this. We can see from the shape of the graph that linearly dependent graphs will have a similar shape at least, and another the dependence we can write for linearly dependence c1 y1 if c1 y1 plus c2 y2 equal to 0. For if y1 and y2 if they are linearly independent, this means this equation is true only for c1 equal to 0 and c2 equal to 0. If this equation is true only for c1 equal to 0 and c2 equal to 0, then these functions are linearly independent. If we can find some value where c1 and c2 are not all zeros, then for which satisfies this equation, then they are linearly dependent. But here if we see, for all positive values of x, they have the same values. This function values will be same. So we can write, say, same values means x square. So it will obtain c1 x square plus c2 x square equal to 0. We will get like this, and from this we can say that c1 plus c2 is equal to 0. That means c1 plus c2 has to be 0 for this equation to be true for all values of x. So we get c1 plus c2 equal to 0. And if we look at the negative region where x takes the negative values, we can see that the first graph and second graph are equal in values but opposite in sign. So that means when we write it, we will get an equation something like c1 x square minus c2 x square equal to 0. So we can see that for this equation to be 0, we should have c1 minus c2 as 0 or c1 equal to c2. So from this we can see that for these two equations, for these 1 and 2 to be true, the only possibility is c1 equal to c2 equal to 0. So from the shape of the graph itself, we can see that no linear combination of this graph will result in 0 for all values of x. So since the positive region have equal values and negative region has opposite values, so we cannot combine those two in any linear fashion so that the result will be 0. So this is the equation wise, this is the situation. So we can say that these two graphs are linearly independent. So this equation is true only for only if c1 is equal to c2 equal to 0. So that is why this the graph is linearly independent. Now that is the first part. This is how we can clearly see this is how these two graphs are linearly independent. But if we check the wronskian, what does wronskian say? Wronskian says wx wronskian is defined as y1 of x, y2 of x, y1 dash of x, y2 dash of x. So wronskian is defined like this. So if wronskian is equal to 0 at all points in an interval, then we can say that these functions are linearly dependent. So this is a good example which shows even though for every real values of x the wronskian vanishes to 0, it will be equal to 0, but still the functions are linearly independent. So this is an example where this is an example that shows that this is not a foolproof method to show both functions are linearly independent. So we will just write down for since we have function x mod x and which has two different functional values for different regions, we will to find the derivative also we have to see. So we will just y2 of x is equal to x mod x, that is equal to, as I read, x square for x greater than or equal to 0 and minus x square for x less than 0. So when we take derivative, the only we can see that this function is smooth, and at x is equal to 0 we can check whether the derivative exists. So y2 dash of x becomes 2x for x greater than 0 and minus 2x for x less than 0. The only confusion will be at point 0. We can see that at the left hand derivative and right hand derivative limit, if you take h tends to 0 plus f of x plus h minus f of x by x plus h minus x, if we calculate the left hand derivative, it will turn out it is x mod x. So it is a we can see here it is a positive function. So and we are applying 0 and it becomes f of h. F of h is h into positive, so it becomes h square minus 0 by x plus h by h, and limit h tends to 0 plus, so we get 0. Similarly, if we check limit h tends to 0 minus of x mod x, we get minus h square minus 0 by h, but still this h get cancelled, and when we apply 0 we will get 0. So at x is equal to 0 also, the derivative exists and it is equal to 0. So we can just put our derivative, either both work, so I just applied here. So x greater than or equal to 0, the derivative is 2x, we can say, and for x less than 0, minus 2x, and for all values of minus infinity to infinity, the derivative exists. So for this function the derivative exists. So we can calculate separately for the wronskian, say 0 to infinity. We can say closed interval 0 to infinity, we will check the wronskian, and the wronskian becomes first function was x square, and second function is x mod x. So using this formula we will do the wronskian. So first function x square into second function, for this is positive values of it becomes x square, and the derivative is 2x, and we can write, we just saw for all positive values it is 2x. So since we have two identical rows, we know that determinant of two identical, when we have such situation we will have wronskian as 0. Similarly for, let's check minus infinity to 0, wronskian will become first function x square, second function is minus x square, and derivative of this is 2x, derivative is minus 2x. So we get minus 2x cube plus 2x cube equal to 0. Wronskian becomes 0 everywhere. For any real values of x, we have seen that the wronskian is 0. So this is a case where the wronskian is 0 for every values of x in the defined interval, but still the given functions are linearly independent. We have seen that going by the definition of linear independence, it satisfies this condition that c1 y1 plus c2 y2 is equal to 0 only when c1 and c2 is equal to 0. So this is linearly independent, but however wronskian vanishes for every real values of x. So this is the solution to question number 51.